So, let us see how to get the marginal distribution. So, let x is a p dimensional random variable, and suppose f x1 x2 xp is the joint distribution function of x1 x2 xp, and suppose I have to get the marginal distribution function of x1 x2 xp minus 1. What it says is, to get the marginal distribution of x1 x2 xp minus 1, consider the joint distribution of x1 x2 xp and take the argument of unwanted variable which was xp to infinity. So, this is same as limit t going to infinity f x1 x2 xp minus 1 xp x1 x2 xp minus 1 t. So, what it says is, if one has to get the marginal distribution, one should get the arguments of unwanted variable to infinity. Now, the proof of this fact is simple. So, let x1 x2 xp minus 1 belongs to rp minus 1. Then this is what I desire, f x1 x2 xp minus 1 x1 x2 xp minus 1, which is the marginal distribution function of x1 x2 xp minus 1. Now, this is same as probability x1 less than or equal to x1 xp minus 1 less than or equal to xp minus 1. Now, I know that if probability of A is 1, then probability of any set B is same as probability of A intersection B. I know that probability of xp less than infinity is 1. So, that is why the probability of this set would be same as probability of this set intersection the probability of a set xp less than infinity, which is 1. Now, xp less than infinity can be written as the set xp less than infinity can be written as union t is equal to 1 to infinity xp less than or equal to t. So, then it becomes this union this, these all were intersections. So, this becomes union t is equal to 1 to infinity x1 less than or equal to x1 xp minus 1 less than or equal to xp minus 1 and xp less than or equal to t. Now, note that with regard to t, this is an increasing sequence, and here it is a union. So, it is a p of limit of these sets, and probability function is continuous. So, this limit can go outside. So, this is same as limit t going to infinity probability x1 less than or equal to 1 xp minus 1 less than or equal to xp minus 1 xp less than or equal to t, which is same as the joint distribution function of x1 x2 xp minus 1 xp at the point x1 xp minus 1 and t, which is limit t going to infinity. So, very interesting result, very useful result. So, what it suggests is, to get a marginal distribution function, take in limit the arguments of unwanted variables in the joint distribution function to infinity. Now, let us consider another useful result, which gives you a way to write down the probability that x takes values in a p dimensional rectangle in terms of distribution function. So, what it says is that x is equal to x1 x2 xp be a p dimensional random variable with joint distribution function as f x x. Then, for any p dimensional rectangle a b, where a b belongs to r p and a is less than b, probability that x belongs to a b, which is same as probability that x I lies between a I and b I, is same as summation k is equal to 0 to p minus 1 to power k. Then you sum over all those z belonging to delta k p a b f x z. Note that delta k p a b is the vertices of p dimensional rectangle a b, in which k a i's are there and n minus k b j's are there. So, let us see what happens for p is equal to 2. For p is equal to 2, x1 greater than a1 less than or equal to b1, x2 greater than a2 less than or equal to b2. So, this would be same as I keep this as fixed. So, x2 greater than a2 less than or equal to b2 is fixed. Then x1 less than or equal to b1 minus probability x1 less than or equal to a1. So, this is what it becomes. It is by additive property of a probability function. Now, I try to look at what is this quantity. So, probability x1 less than or equal to b1, x2 greater than a2 less than or equal to b2. This would be same as I keep this as fixed. So, x1 less than or equal to b1, x1 less than or equal to b1. Then probability x2 less than or equal to b2 minus probability x2 less than or equal to a2. So, in fact, if you try to look at what the result indirectly which we are using is, if A is subset of B, then probability of B minus A is same as probability of B minus probability of A, or in other words, probability of B is same as probability of A plus probability of B minus A. So, for example, in this case x1 less than or equal to b1 x 2 greater than or equal to a 2 less than or equal to b 2 is contained in this set, and that is how you get this. So, you can just see this. This is a simple algebra. So, now let us write down this quantity. So, that is same as f x 1 x 2 b 1 b 2 minus f x 1 x 2 b 1 a 2. So, just see this is same as probability x 1 less than or equal to b 1 x 2 less than or equal to b 2, which is f x 1 x 2 b 1 b 2 minus f x 1 x 2 b 1 a 2. That is what I have written over here. Now, let us look at the second term, which is probability x 1 less than or equal to a 1 x 2 greater than a 2 less than or equal to b 2. So, I keep x 1 less than or equal to a 1 fixed. Then this is same as x 1 less than or equal to a 1 x 2 less than or equal to b 2 minus x 1 less than or equal to a 1 x 2 less than or equal to a 2, which is same as f x 1 x 2 at the point a 1 and b 2, then f x 1 x 2 at the point a 1 and a 2. So, your final expression probability x belonging to a b is the difference of this and this. So, the difference of this and the difference of this, which is same as f x 1 b 1 b 2 minus f x 1 b 1 e 2, which comes over here, minus f x 1 a 1 b 2, which comes over here, and then plus f x 1 x 2 a 1 a 2. So, you see this is same as when 0 of them are coming as ai's, which is this term, which comes with the minus 1 to power 0 as a positive sign. So, f x 1 x 2 b 1 b 2. Then one of them is a 1 ai, so which comes through this, but that comes with a negative sign. So, minus 1 to power 1, which is this. I am summing over all the such vertices. Then finally comes k is equal to 2, which comes with minus 1 to power 2 positive sign, and where both of them are ai's, which comes with a positive sign f x 1 x 2 a 1 a 2. So, thus the result is true for p is equal to 2. Assume that the result holds for any probability function for p is equal to m. So, using this I will prove the result for p is equal to m plus 1. So, to do that I will have to consider the m random variables x 1 x 2 x m plus 1. So, let us denote this vector by vector y, which is nothing but vector x, which is x 1 x 2 x m. So, which is vector x, which is x 1 x 2 x m and x m plus 1. Similarly, denote a 0 as a 1 a 2 a m, b 0 as b 1 b 2 b m. A is a 1 a 2 a m and a m plus 1. So, that means a in a sense is nothing but a 0 comma a m plus 1. Similarly, b turns out to be b 0 vector and b m plus 1, which is nothing but b 1 b 2 b m, which was nothing but b 0 and b m plus 1. Then probability that y belongs to a b, which is same as probability that x comma a m plus 1 belongs to a 0 a m plus 1, which is same as x belongs to a 0 b 0 and x m plus 1 belongs to a m plus 1 b m plus 1. So, I use the conditional probabilities. So, this is same as probability x belongs to a 0 b 0 given x m plus 1 belongs to a m plus 1 b m plus 1 times probability x m plus 1 belongs to a m plus 1 b m plus 1. Now, note that conditional probability function is a probability function, and here x has only m components. So, I can use here the result for m for the conditional probability function. So, using the result for p is equal to m for conditional probability function, we have probability x belonging to a 0 b 0 given x m plus 1 belongs to a m plus 1 b m plus 1 is same as summation k is equal to 0 to m, z belonging to delta k m a 0 b 0, probability x less than or equal to z, which is a conditional distribution function given x m plus 1 belongs to a m plus 1 b m plus 1. So, I have simply used the result for p is equal to m. So, that means over here this quantity can be replaced by this quantity. So, to get this whole quantity I have to multiply it by probability x m plus 1 belonging to this, which is same as this multiplied by probability x m plus 1 belonging to a. So, that is same as probability of a given b into probability of this, which will be same as probability of this intersection this. So, probability y belonging to a b, that is y, which is over here, is nothing but this conditional probability multiplied by this, which becomes joint probability, which is probability x less than or equal to z and x m plus 1 greater than a m plus 1 less than or equal to b m plus 1. Now, I keep this as a fixed and I write down this as probability x less than or equal to z, x m plus 1 less than or equal to b m plus 1 minus probability x less than or equal to z, probability x m plus 1 less than or equal to a m plus 1. So, that is what I do next. Summation k is equal to 0 to m, delta k m a 0 b 0, probability x less than or equal to z, x m plus 1 m b m plus 1 minus probability x less than or equal to z, x m plus 1 less than or equal to m plus 1. Now, if you see over here, what is happening? In this, k of z i's were from first to m a i's, and x m plus 1 is less than or equal to b m plus 1. So, when I go from m to m plus 1, x m plus 1 gets added. Now, x m plus 1 can contribute in this joint term through x m plus 1 less than or equal to b m plus 1 or x m plus 1 less than or equal to a m plus 1. When x m plus 1 is less than or equal to b m plus 1, then the power remains the same, because number of z i's is still the same. So, minus 1 to power k z belongs to delta k m a b. Now, when it becomes over here, number of a i's has increased by size 1. So, that is why if you combine these terms, you will get this quantity. So, you can see from a 0 b 0 to I go to a b. So, this is first. So, for example, if you have to break this, what I do is I first write down this as k is equal to 0 to m, and then the same thing, but then x m plus 1 is less than or equal to b m plus 1, because the mth one can be either z m plus 1 can be either b m plus 1 or a m plus 1. So, when z m plus 1 is b m plus 1, so that is the case summation k is equal to 0 to minus 1 to power k, and I break it when the z m plus 1 is a m plus 1, that would come with a minus sign over here. So, this becomes, this is a simple algebra, you can verify this. I have given you enough hint, but still you can verify that these two quantities are same. So, this same as summation k is equal to 0 to m plus 1 minus 1 to power k z belonging to delta k m plus 1 a b minus 1 to power k f x z. So, basically probability that x belonging to the p dimensional rectangle a b, one can get through distribution function as summation k is equal to 0 to m minus 1 to power k summation z belonging to delta k m a b minus 1 to power f x z. This will not be minus 1 to power k over here. So, if one has to get probability x belonging to a b, one can get through distribution function using this expression. Now, let me give this as a take home problem. So, let x equal to x1 x2 be a random variable with joint distribution function given by this. These are the different branches. Find the marginal distribution functions of x1 and x2. So, as I have told you, to get the marginal distribution functions, one has to take the argument of unwanted variable going to infinity. Now, before I take the second take home problem, consider a joint distribution function given by this. Verify whether or not summation k is equal to 0 to 2 z belonging to delta k to a b f x z1 z2 is greater than or equal to 0 or not. Now, if it was a distribution function, then we know that this property would always be satisfied. I am saying that you verify whether this property is satisfied or not, because there is a possibility that this is not a distribution function, but still this is property is satisfied. So, verify if this property is satisfied or not. Suddenly, if this property is not satisfied, you can directly argue that this is not a distribution function. So, take this as a exercise. Before I finish this module, let me give a summary of the things I will be doing in the next module. So, we will derive various properties of joint distribution function. The way we derived the properties of a univariate distribution function, we will derive various properties of joint distribution function. So, this was all for this module. Thank you for your patience and have a great day.